All right, so we want to focus now on part D. We figured out A through C. Find the number of cells after 4.5 hours. Well, that shouldn't be too bad. We've got our formula for the population at any time, and so when we want to figure out what part D is, we just plug it in. We just plug it in and we get P of 4.5 is going to be 50 e to the 1/2 natural log of 8 times 4.5. And when you work this out on your calculator, you're going to get approximately 5,381.74. I've never seen a 0.74 of a bacteria cell, but that's what the math says. And now, if you think about it, you should check and make sure this makes sense. So at 2 hours, let's go back up. At 2 hours, we had 400. And at 6 hours, we had 25,000. And so our answer for 4.5 hours better be somewhere between these two. And sure enough, it is. So if we had gotten an answer of, less than 400 or more than whatever it was 20, I lost my paper here, 25,000. So if you've gotten something bigger than 25,000 or less than 400, then you know there's a problem. Okay, let's scroll up now and look at part E. Part E says find the rate of growth after 4.5 hours. This is not talking about the relative growth rate K. This is not talking about K. It's just talking about the general derivative. It's saying find the derivative of after 4.5 hours. So let's scroll down and we'll do part E. Part E is asking for P prime of 4.5. And so one method you could do is you could actually write down, well, P of T equals P naught e to the 1/2 ln of 8 times T, and you could compute P prime and you use the chain rule and kick this down. That's all fine and it works and it's no problem. You can do that. But I want you to realize something. You know that P prime of T, this is K times P of T. That's the assumption of the problem. And so you can use that because it makes it pretty straightforward here. You know that P prime of 4.5 is K, which was what, 1/2 ln of 8 times P of 4.5. We just computed P of 4.5 in the above problem. And so you can plug everything in here and you can come up with, well, let's see, it's going to be 1/2 ln of 8 times the answer that we got above, 5,381.74. We should put a parenthesis here, otherwise it's going to be hard to keep track of. And so when you do that, you're going to get that this is roughly 5,595.5. And so that's the growth rate. We're growing at 5,595.5 bacteria per hour. Our units here are hours. So that's the rate of growth per hour. So after another hour, you'd expect to roughly add that many bacteria. Of course, the growth rate is changing, right? Every moment that passes, the growth rate is a bit faster, but this gives you an estimate using the tangent line. Okay, last question. We want to figure out question F. So it says, when will the population reach 50,000 bacteria cells? And so hopefully you know how to do that. For part F, you want to solve. It's a when, so I'm solving for T. P of T equals 50,000. And so I get, well, 50 e to the, I'm going to write it as ln of 8 over 2 times T equals 50,000. And so I can divide out the 50 and I get e to the ln of 8 over 2 times T equals 1,000. Take the natural log of both sides. The natural log of this side cancels, leaving you just the exponent. And of course I get a natural log of 1,000. So my next line looks like ln of 8 times T over 2 equals natural log of 1,000. And so of course T is going to be 2 natural log of 1,000 divided by the natural log of 8. You can use your calculator and you're going to get roughly 6.64386 hours. So roughly 6 hours, we're going to have 50,000. By the way, I don't know if anybody else is alarmed, but the thought of a bacteria growing that fast is rather scary. I'm sure it's very common, but it's a little terrifying. So there you go. That's 3.3. You've got just a couple of homework problems to knock out, and we're on to the next section. Ciao.